Hi guys, and welcome back to 7 Steps to a 7 in Olympiad number theory. In this video, which is the final video in the series, we're going to be talking about constructions in number theory. In other words, how to construct positive integers which satisfy a certain requirement, and look at some of the theorems that can be used to construct them, and some of them are called sledgehammers. And to get a sense of the problem that I'm going to talk about, let's go ahead and take a look at a recent example of a construction problem. And it goes as follows. Suppose that n is a positive integer, then you must show that there exists a value k such that a1 factorial plus a2 factorial plus so on and so forth plus an factorial plus k is never a perfect square for any a1, a2, all the way to an. So no matter what choice I choose for those guys, this will never be a perfect square. Now this problem is super hard to solve, and I think it's way beyond the scope of this video. But you can go ahead and try it on your own after watching this video. But the point is that these types of problems appear very often inside number theory, so it's good to know how you would approach them in the first place. So without further ado, let's get right into it. So how exactly do all of these construction problems work? And here's a secret, and it is that all of these basically have the same structure. And what exactly do I mean by same structure? Well, here's the basic setup. So first you have to, suppose you want to find a number n which satisfies a property. So the first thing you do is to try working backwards and try deducing whatever you can about n. So for example, if you want to prove that n squared plus 1 is prime for infinitely many n, then you must know that n is even. Because if it's odd, then it's obviously divisible by 2 when n is large enough. So that's what I mean by working backwards, where you can just extract conditions from n to continue going. And then the next step is if you have a bunch of properties, so properties are sufficient. In other words, if all the properties are satisfied and that makes your number n work, then you're done. And if your properties are not enough for n to satisfy the problem statement, then let's go on to step 3 of the solution, which is to try making additional assumptions. So in the case of n squared plus 1 being prime infinitely often, we can try making an additional assumption about n. For example, we could assume that n is equivalent to, say, 1 mod 5. And that might simplify the computation a lot. And 4, you then just keep repeating the process. And when you repeat the process is if you get a class of working n, then that means that you're done. Otherwise, you go back to this step here, or go back to this step here, or go back to this step here. And I forgot one final step that you have to do, so I'll call this step 0, which you have to do before the problem begins, is to try small n and to get a sense of the problem and see which work and which don't. And that way you have a good sense of what you have to do in the problem and what must be true in order for it to hold. Okay, so this is the basic structure of a bunch of problems. So here's an example that should be familiar from the second video, and it is this problem, where we must find a value of n which doesn't work, or we must prove the assertion. Now, for the solution to this problem, I'm going to redirect you to the video 2 if you haven't seen that already. which you hopefully have and have seen the example solution at the end. But the main things I want you to get away from this is that we reduce this condition to a simpler condition. So 2n mod n being odd. And then after that, we prove things about n. For example, n is odd and n is composite. And it feels like we had enough of these conditions already and we couldn't really get much else. And then we just tested values of n until they worked. And that gave the solution. And the magic value of n, if you're curious, was n equals 25. Now, usually the final step is not to guess and check the value of n, because in this case, this is kind of an anomaly. And indeed, inside most cases, in most of the construction problems you end up solving, you almost never find the exact value of n. Instead, you have to show one exists. Now, how exactly do you show a number n exists without finding it? And the way we do so is by using a bunch of key theorems, which allow us to construct very weird n according to our tastes. So let's go ahead and take a look at them. The first of these key theorems should be really, really familiar to you, as it is none other than the Chinese remainder theorem. Now, I discussed what the Chinese remainder theorem was inside the first video, but as a recap, here is what it is. So suppose we have a bunch of numbers n1, n2, all the way to, suppose, nk, and all of them are relatively prime with one another. So none of them have a common factor. Then suppose we have the system of congruences a1 mod n1 and a2 mod n2, and so on and so forth, all the way to ak mod nk. Then that means that if we want to find a number n which satisfies all of these, then the Chinese remainder theorem tells us that such a number exists. And notice that the Chinese remainder theorem does not tell us what the number n is. So we don't know what it is. But the only thing that matters is that it exists. And this makes it especially useful for construction problems. So as an example of how it can be used, let's take a look at this problem here. A set of positive integers is called fragrant if it contains at least two elements and each of its elements have a prime factor in common with at least one of the others. Let p of n be n squared plus n plus 1. What is the least possible positive integer value of b such that there exists a non-negative integer a for which this set here is fragrant? Now this problem should be familiar from the video 5 exercises. So if you haven't already, go ahead and try this problem out. And hit the play button whenever you want to go ahead and discuss it. So hopefully you've tried out the problem by now. So let's go ahead and go through it. Now, I'm going to go ahead and gloss over a bunch of details since they aren't super relevant to this video. But here are the main things you'll need to know. So first thing is GCD of p of n and p of n plus 1 is always equal to 1 for all numbers n. And by the way, I encourage you to work through the proof of all of these facts I'm providing here using the Euclidean algorithm. And then GCD of Pn and P of n plus 2 is always greater than 1 if and only if n is equivalent to 2 mod 7. And then GCD of P of n and P of n plus 3, well, that is just greater than 1 if and only if n is equivalent to 1 mod 3. And finally, what about P of n plus 4 now? Well, that's greater than 1 if and only if n is equivalent 2, 7 mod 19, I think. Yeah. So these are the facts that we're going to be assuming for now. You can go ahead and prove all of them with the Euclidean algorithm. But that's not the important part here. The point is, how can we find a value of A which works for the B if it exists? Well, let's go ahead and try solving the problem. So can we get away with B equals 1? Well, we can't because it has at least 2 elements. So I'll go ahead and put this in the corner. That doesn't work. Then B equals 2. Then we have 2 adjacent elements, P of A plus 1 and P of A plus 2. But we know they are relatively prime. So that means that they can't have a common prime factor. So that doesn't work at all. So what about B equals 3? Then that means that we have P of A plus 1, P of A plus 2, and P of A plus 3. And inspired by the fact that B equals 2 doesn't work, we want to somehow use the fact that we have a middle element here, which must be paired up with one of these adjacent elements, which doesn't work because of this item here. So that B equals 3 doesn't work. What about B equals 4? Well, we have P of A plus 1, P of A plus 2, P of A plus 3, and P of A plus 4. Then that means that these two have to be paired together because, as I said earlier, we can't have these ones paired together because otherwise we get a contradiction according to this one here. So these two are paired together, which implies A plus 2 is equivalent to 2 mod 7 by this one over here. And likewise, these two are paired together, so A plus 1 is equivalent to 2 mod 7 as well. But then that means that these two are equivalent mod 7, which is impossible since they're different by 1. So we have worked through the B equals 4 case, and this doesn't seem to work. Now let's take a look at B equals 5. So P of A plus 1, P of A plus 2, P of A plus 3, P of A plus 4, and P of A plus 5. Does this work? We're motivated to think that it might work, so let's see if it does. And again, we want to try looking at the middle elements. In this case, the P of A plus 3 can't be paired with this one here or this one here. So it has to be paired with one of the outer elements. And without loss of generality, because this is pretty symmetric, we can assume that it gets paired with this one here, because tackling the case where it's this one over here is very similar. So that means that these two are paired up. So A plus 3 is equivalent to 2 mod 7. And now see what the A plus 4 can be paired up with. This A plus 4 here must be paired up with one of these guys here, either A plus 2 or A plus 1, because A plus 3 and A plus 5 don't work by this one here. But if this one was paired up with that one, then that means that A plus 2 is equivalent to 2 mod 7. And that contradicts what we had earlier with A plus 3. So that means that it has to go to that one. So that means that we have all of these guys here. Now let's take a look at P of A plus 2. Then P of A plus 2 must be either paired up with, can't be A plus 1 or A plus 3. If it's A plus 4, then this means that P of A plus 2 is equivalent to P of A plus 4, and A plus 2 is equivalent to 2 mod 7. And that, again, doesn't work. And I forgot to say that because we have P of A plus 4 and P of A plus 1 together, A plus 1 is equivalent to 1 mod 3. Forgot to say that earlier. And then because we can't have P of A plus 2 and A plus 4, we have that these two are paired together. And that means by this item here, that A plus 2 is also equivalent to 1 mod 3. and this does not work again. So we have gone through all the possible cases, or just tried continuing to do whatever we could. We figured everything we could about the number a, and in this case, we got something that just didn't work. So hopefully you can see the construction philosophy coming into play now. And now let's take a look at b equals 6. Then we need p of a plus 1, p of a plus 2, all the way to p of a plus 6. I'm actually going to write all of them out because it will be better this way. And p of a plus 6. This might be able to work, who knows. And something you might have noticed about what we were doing earlier is that if we had two numbers paired together and we had two other numbers paired together, which were the same distance apart, then that means that a plus 1 is equivalent, in this case, to mod 7, but so is a plus 4, and that's bad. So that means that we want all like the pairings to have different lengths. So with this in mind, let's go ahead and try pairing things up. So let's suppose that p of a plus 1 here is paired up with p of a plus 5, for instance. If this doesn't work, then we can always choose p of a plus 6. Then p of a plus 2 can't really be paired with p of a plus 6. So it has to be paired with one of the middle numbers. And it can't be p of a plus 3, obviously. So it has to be this one. And that leaves these two. So we end up getting the GCD of this one and this one here is greater than 1. So a plus 1 is equivalent to 7 mod 19. And then we get also, because p of a plus 2 and a plus 4 paired together, a plus 2 is equivalent to 0 mod 7, or 2 mod 7. And finally, because p of a plus 3 and p of a plus 6 are paired together, we have a plus 3 is equivalent to 1 mod 3. So now we have all of these congruents here, and if a number a satisfies all of these, then we are set, because then we have all of these pairings, and by this work over here. But how do we know such a number exists? Well, if we solve each congruence separately, we end up getting something like a is equivalent to 6 mod 19, a is equivalent to 0 mod 7, and finally a is equivalent to 2 mod 3. And how do we know that such an a exists? Well, because 19, 7, and 3 are all relatively prime to one another, this means that such an a exists by the Chinese remainder theorem. And because such an a will give us the fragrance that we need, that means that b equals 6 is our answer. And note that we never even needed to find the value of a in this case, because we just needed to show it existed. And if you're curious, by the way, the value of a that ends up resulting is 196. But that's irrelevant for the problem. The point is that we did not need to know the exact value of a, we just needed to know it exists. And this is a very common idea in construction problems, as I said earlier. Now, oftentimes you're not going to get away with the Chinese remainder theorem on its own. So you have to end up using some other key theorem. And what key theorem do you end up using now? And the answer is you have to use some very technical and hard to prove theorems. And because they are super, super hard to prove, and their proofs often take pages, they are called sledgehammers. Or that's how they're informally called inside the Math Olympiad community. And we're going to be talking about these sledgehammers shortly. But let me give a brief warning about sledgehammers in general. So John Berman, the leader of the USA IMO team, told me that if you use any sledgehammer in a solution, you don't understand the problem entirely. And while I disagree with him because these sledgehammers are super, super, super hard to prove, he does make a good point. And it is that you should always try avoiding the sledgehammers. So sledgehammers. you always want to try avoiding them because otherwise you're just going to have an incredibly complicated solution. But again, if the solution ends up using these sledgehammers in a natural way and it feels very natural to use them, then, well, you must do what you must. And now let's go ahead and look at these sledgehammers. So the first one of them is Bertrand's postulate, which states that there's always a prime number between n and 2n for all positive n. So this is called Bertrand's postulate. And essentially this allows us to construct primes to our advantage by constructing a prime like this and therefore getting what we want. Now the second sledgehammer is called Dirichlet's theorem. So suppose that A is equivalent, suppose we have A mod M, just like the CRT setup, and such that GCD of A and M is equal to 1. Then this means that there exist infinitely many primes P equivalent to A mod M. And this is infinitely many. And this theorem is called Dirichlet. And Dirichlet is especially important because you can always use Dirichlet's theorem in tandem with CRT, because you can get a bunch of modular relations that P ends up satisfying. Then you know that a residue solution exists via the Chinese remainder theorem, and then you can end up constructing a prime P by using Dirichlet's theorem. So that's the second sledgehammer. The third one you need to know about is called Kobayashi's theorem. And the following few theorems we're going to be talking about use something called the prime divisor set. So prime divisor set is if you have a set S, then it is a set of all primes P such that P divides the number S inside the set S. And this is set of all. For example, if you have the powers of 2, 1, 2, 4, 8, so on and so forth, then the prime divisor of the set is just 2. While if you have 1, 2, all the way to infinity, 3, 4, then the prime set divisor set of this is just all primes and is infinite. Anyways, let's go ahead and discuss the rest of our sledgehammers. So the first one is called Kobayashi. And it states that if the prime divisor set of S is finite, so prime set of S finite, then if we add a constant to every single element of S, so I'm going to call this S plus A, then the prime divisor set of this set here is infinite. And this has some profound consequences. For instance, over here, we know that if we have 1 plus 1, 2 plus 1, 4 plus 1, 8 plus 1, so on and so forth, Kobayashi's theorem basically guarantees that infinitely many primes divide some number in this set. So that's Kobayashi's theorem. So now let's take a look at our next sledgehammer, which is Zsigmondy's theorem. And what this states is, suppose you have positive integers a and b, and you consider the numbers a minus b, a squared minus b squared, a cubed minus b cubed, and so on and so forth. Then what Zsigmondy's theorem says is that there always exists one of these numbers here, which then Zsigmondy's theorem states that every single number here has a primitive prime divisor. So P divides it, but P does not divide this one or this one. So we're always going to be adding a new prime every single time. That's what Zsigmondy's theorem says. Well, except for two very, very special cases. And it is a case where A plus B is a power of 2. And then the power of k, the power of k is equal to 2. So we're looking at a to the k minus b to the k. And the second case where this doesn't hold is where a equals 2, b equals 1, and k equals 6. Because 2 to the 5 minus 1 equals 31, and 2 to the 6 minus 1 equals 63. And the numbers 3 and 7 appear because 2 cubed minus 1, and then 2 squared minus 1. So that's the reason why it doesn't work in those cases. And this is the form of Zsigmondy's theorem. It works on every single other case. And then we also have another form of Zsigmondy's theorem. So this is form 1. Then we have form 2 of it, which states that if we look at a plus b, and then a squared plus b squared, and so on and so forth, then we again have this primitive prime divisor thing. So if we have like a to the 5th plus b to the 5th there, we have p divides it, but p does not, p does not, p does not, and p does not here. And this holds for all positive integers a and b, and the exponent k here, unless we have a equals 2, b equals 1, and k equals 3. Because then we have 2 plus 1 is 3, 2 squared plus 1 is equal to 5, 2 cubed plus 1 is 9, and which is 3 squared, and the 3 was already covered here. And it always holds in the other cases. So that's Zsigmondy's theorem. And now let's take a look at our final sledgehammer, which actually isn't super hard to prove, and it is called Schur's theorem. And what Schur's theorem states is that suppose you have a polynomial p of x, which is not constant. Then the prime divisor set of p1, p2, all the way to infinity, so prime divisor set, it is infinite, so long as this is non-constant. So what basically every single one of these theorems has been telling us is that we can construct a prime that satisfies a very nice property and therefore can be exploited by us in these problems. And that's the main reason why we want to use these sledgehammers. And sledgehammers can be used outside of constructions. And let's take a look at some easy examples for how they can be used. And you should try solving these on your own. So the first one is prove that the set 1, 2, all the way to 2n can be partitioned into n pairs of 2. So like 2n can go to 1, and so on and so forth, such that the sum of the numbers in each pair is prime. And the second one is from the USAMTS, which asks you to find all solutions to 2 to the a, 5 to the b, minus 1 equals 3 to the c, where a, b, and c are non-negative integers. And both of these can be solved using sledgehammers, even though they're not construction problems. So be on the lookout for whenever these sledgehammers can be used. So let's go ahead and see some other methods. I'm not going to go over them extensively, but here are some other ways that you can solve construction problems. And the first way is that there are infinitely many integers. And the point is that because we have infinitely many of them, we can just keep using them and using them and using them, or take a number to be incredibly large and we won't run into issues. So we want to use them well. And the second idea that we can use is instead of just going straight for the kill with that construction, we can just build things up one at a time. But what I mean by building up is that we can go from 1 prime factor to 2 prime factors and so on and so forth, or we can start with a smaller number and go to a larger number and just keep going that way. So the point is that you should keep these two in mind here. And I want you to see if you can apply each of these ideas inside the exercises or in the example coming up. So here's the example we're going to be looking at, and it's from the 2000 IMO. Does there exist a positive integer n with exactly 2000 distinct prime divisors? And n divides 2 to the n plus 1. So go ahead and pause the video and try this problem out on your own. And when you're ready to discuss with me, hit the play button and we'll discuss. So hopefully you've tried out the problem on your own. So let's go ahead and look at it together. So 2000 prime divisors seems like a very, very scary number. So let's go ahead and see if we can start smaller. So if we have one prime divisor, then we know that we have 1 doesn't work, 2 doesn't work because it's even, 3, well, 3 divides 2 cubed plus 1, which is 9, which is true. So our magic number when we have one prime divisor is 3. And what if we have 2 prime divisors? Well, suppose we have our number like 2 to the p cubed. And we're just going to assume that we have like 1 prime here and 1 prime here, and the 2 primes are different. Then we have p cubed divides this plus 1. And if we look at p and q separately, remember we can do this by using the Chinese remainder theorem as explained inside the second video. We have that p divides 2 to the p cubed plus 1. We can simplify this exponent by using Fermat's little theorem if we want. So we get p divides 2 to the q plus 1. Similarly, q divides 2 to the p plus 1. And this means 2 to the q is equivalent to negative 1 mod p, or 2 to the 2 cubed, if we square both sides, is 1 mod p. So this requires that the order mod p of 2 divides 2 cubed. And because q is prime, this requires it to be either 1, 2, q, or 2 cubed. And if we have that, if it's any of these two here, and if we have that the order is equal to 1, then that doesn't work because 2 is equivalent to 1 mod p. That doesn't work. If it's 2, then 2 squared is equivalent to 1 mod p, or p is equal to 3. And this might end up working, but we'll have to see. So we're going to ignore this case for now. If the order is q, then that means that this is equivalent to 1, which isn't true. So therefore, the order must be equal to 2 cubed. And as a consequence, we know it divides p minus 1. And similarly, we also know that 2p divides q minus 1 as well, in the case where neither is equal to 3. And this makes us think that we're going to get into some sort of size issue. And indeed we do, because this means 2 cubed is less than or equal to p minus 1, and this is less than or equal to like 2p minus 1, which is less than or equal to q minus 2. And we know that's just not going to work at all. So therefore, p times q doesn't seem to work. What on earth is going on? So at this point, we're motivated to try adding on one other prime factor. Suppose p squared times q. And because we have p squared times q, and we saw how difficult it was to analyze a case where p and q were arbitrary, so let's try setting p and q, one of p and q to be some fixed value. And in this case, because we have one prime divisor here, let's try setting one of these two to be equal to 3. So let's try setting p equals 3 first, so that we have 9 times q. Then we want 9q to divide 2 to the 9q plus 1. And can we do this? Well, we know that we should consider each congruence separately using the Chinese remainder theorem. And with that, we get 9 divides 2 to the 9q plus 1, or 2 to the 9q is equivalent to minus 1, 1, 9. And if we use Euler's theorem to simplify this one here, because 2 to the 6 is equivalent to 1 mod 9, we get that this is 2 to the 3 times q is equivalent to negative 1. But wait, because q is odd, that means that we know that this is either going to be 3 or 0 mod 6. And we can just eliminate all the other factors of 6 by using this. So it's either going to be 3 or 0 mod 6. But because q is odd, that requires it to be 3. So we get this is equivalent to 2 cubed, which is equivalent to negative 1 mod 9. And this is true. So now we just have to deal with the case that q divides 2 to the 9q plus 1. And with that, we end up getting, by Fermat's little theorem, that this can be 2 to the 9. In other words, q divides 513. And q must not be equal to 3. Now, if you factor 513, you end up getting something like 9 times 57, I believe. And this is also 27 times 19. So we can just take this 19 here. So q equals 19. So therefore, our number that has 2 prime divisors that seems to work is 3 squared times 19. And this works by using the Chinese remainder theorem. So now let's move on to 3 primes. And because we don't want to do all the work that we did with the 2 prime case, let's try adding on a prime this time, because we're lazy. So this becomes 3 squared times 19 times some new prime, which I'm going to call p. Then we know that this divides 2 to the 3 squared times 19 times p plus 1. And again, we want to use the Chinese remainder theorem to our advantage. So let's try looking at modulo 3 squared first. If we look at that, we want to show 2 to the 3 squared times 19 times p is equivalent to negative 1 mod 3 squared. But remember that because we're taking from this 2 prime divisor case, that if we eliminate that, it's still equivalent to negative 1. So we can introduce the factor of p here by taking both sides to the power of p. And we can assume that p is going to be odd, because, well, the only even prime is 2, and this is an example of an extra assumption that we make. So in other words, we get that this is equivalent to negative 1. So it works modulo 3 squared. And it works similarly by taking modulo 19. And you might be wondering, can we just combine those 2 steps into one? Well, yes, we can, because 2 to the 3 squared times 19 times p is equivalent to, we want to show as negative 1 mod everything but the p part. And we know that if we get rid of this p here, this is true because it works in this case. So we can just take both sides to the p power, and this is negative 1. And therefore it ends up working modulo 3 squared times 19. And now we just have to fulfill the mod p requirement here. So that means that p divides 2 to the 3 squared times 19 times p plus 1. And then we can use Fermat's little theorem to get rid of this one here. So that's 3 squared times 19 plus 1, which is, I think, 2 to the power of 171 plus 1. And we want p to not be equal to 3 or 19. And how do we know such a prime p exists, which is not equal to either of those two? Well, for one, you could just bash it out, I guess. But here's where another key theorem comes into play. We want a number p dividing some number of this form. And this heavily reminds us of Zsigmondy's theorem, where we can always find this primitive prime divisor that is not a divisor of any other number in the sequence. And because we have a new prime divisor every single time, we have so many to choose from. And obviously we can choose one that is not 3 or 19. And this gives us our prime p, and therefore the 3 prime case is resolved. Can we generalize this idea? Well, yes, we can. So specifically, suppose we have our k prime divisors, and we have its 3 squared times like 19, which I'm going to call p2 for now. Then our prime p that we found earlier, which is p3, and so on and so forth, all the way to pk. So we have k prime divisors here. And then we want to add, and we know that this divides 2 to the 3 squared times p2 times all the way to pk plus 1. And now we want to add another prime number here, p2, p3, all the way to pk, and then another one, p to the k, pk plus 1. It divides 2 to the 3 squared p2 all the way to pk, then pk plus 1, and then plus 1. And we can look at this using Chinese remainder theorem again. If we look at it modulo this one here, then we might expect something similar to work out here. So we want to show 2 to the 3 squared p1, p2 all the way to pk plus 1 is equivalent to negative 1 mod 3 squared p2 all the way to pk. And we know that if we get rid of this p1 here, then it is true because of this one here. So we can just take both sides to the pk plus 1 power, so pk plus 1. And that's true. So once again, we just have to deal with the case where pk divides this enormous expression, or pk plus 1, I guess. And again, using Fermat's little theorem, we can get rid of this one here. And this gives k plus 1 divides this humongous thing, and it is not equal to 3p2 all the way to pk, because we want to introduce a new prime factor. But by Gigmondi's theorem, because this number is so enormous, we can always choose a prime pk plus 1, which fits the bill. And this will allow us to finish the problem, because we can end up getting a new prime divisor every single time. So from 3, we can get to 4, from 4, we can get to 5, and so on and so forth, until 1999 gets us to our magic number 2000. And that solves the problem. Now, one thing I want to point out about this proof, and it goes along with the idea as I said in the video, is that we never explicitly found the value of n. We just showed that it exists. And that's the key idea in many construction problems. You just have to show it exists. Now, of course, you can always find the exact value of n, and that also works to solve the construction problems. But sometimes you just don't need to know exactly what it is. And this also highlights the key idea where you take it one step at a time and build it up one prime at a time. And we use Gigmondi's theorem as a key theorem in order to construct a new prime every single time. And this is an example of a sledgehammer used in a construction problem. So now I've provided a bunch of exercises inside the corresponding handout to this video. So please go ahead and try out those exercises regarding constructions. And you might have noticed that I included a bunch of other problems at the end after the construction part, because congratulations, you finished the number theory course. And I want to give general practice for number theory. And warning, the problems at the end are super, super hard, so you should take your time with them. And a bunch of the problems also uses sledgehammers as discussed earlier, but I'm not going to tell you which ones they are. And they're roughly in order of difficulty. And now what do you do? And there are many options you can choose from. For example, one option is that you can just keep doing easy problems until you get solid with them. And that's not a bad idea because often you're going to just be seeing these easy number theory problems and you want to be able to solve them consistently. And oftentimes, consistently is better than being able to learn a lot more. However, at some point, you should also consider learning more advanced theory. And this course has technically taught you almost all the number theory you'll need to know for the purposes of math Olympiads. But there's an entire world of number theory out there, featuring ideas such as like quadratic reciprocity, analysis, Vieta jumping, so on and so forth. And my suggestion for learning these concepts is to only have one goal in mind, is to keep learning and have fun with it. Do not learn the concepts just because they're going to be useful for your Olympiad. Instead, I want you to learn them if you genuinely think they're cool concepts and want to have fun with them. Because that's the only way you're going to learn them. And if you only want to learn them to solve the harder problems, you'll not get anywhere. And one final thing is that, as I said earlier, the course has taught you the concepts necessary for Olympiads. So you might be asking why I'm not able to solve problem 2s. Like why you'd not be able to solve them. And even though you know all the concepts required. And my answer to that is to simply practice. Practice makes perfect. And the more and more you practice, you'll be able to build your intuition much, much more. And you'll be able to often realize what exactly a problem requires without working through the details, visualize the numbers interacting with each other in your head, and so on and so forth. And I could go on and on about how to practice, but I've linked some resources on practicing inside the handout. So I hope my course has offered you a glimpse into the world of Olympiad number theory, and it has enabled you to look at any number theory problem with a positive outlook. And happy solving! Thank you so much for taking my course. Please subscribe if you'd like to see more videos, and I hope to see you guys soon.